Welcome to Homework Lib.
We have two samples here, and we want to know if there's a significant difference in the mean lifespan. So we're going to start by stating our hypotheses. The null hypothesis represents no change, no difference. So here, it would be that the mean lifespan for the Philips bulbs is equal to the mean lifespan for HMT bulbs. The alternative is the opposite of that there is a difference between the population means. Now we have two samples to help us out here. We have sample 1 from Philips, which has 50 bulbs with an average life. So a sample mean of 1,500 and a sample standard deviation of 60. Sample 2, size 50, mean 60, 1,512, and standard deviation 80. Now, to perform a hypothesis test, you start by pretending the null hypothesis is true. Pretend that these do come from populations with the same population mean. And then you look at the sampling distribution. If I were to take every sample of 50 Philips bulbs, take the sample means and plot them out, I would get something approximately normal, thanks to the central limit theorem. Same for the HMT bulbs. Now, the difference between two normal distributions is also normal. So, the distribution of the possible differences in sample means that I would expect to see is approximately normal. Its mean is mu p minus mu h. Its standard deviation is a little bit more complicated. Root sigma p squared over np plus sigma h squared over nh. So it's the pooled standard error. So this is for the difference in possible sample means. Now, where would my samples fall on here? We can see this difference of 12 or minus 12, the way I've written it. Doesn't really matter either way. Now, maybe that would fall here, in which case I could say, yeah, there's a difference in our sample means, but that wasn't unlikely. It could have just appeared due to chance, just sampling error. And the population means are actually still the same. Since that's plausible, we don't reject the null hypothesis there. But if our difference is way out here, I would say, wow, if the population means are the same, if the null hypothesis is true, this is really unlikely to happen. Therefore, I don't think it's true. And then you reject them. The cutoff point where something becomes so unlikely that you reject the null hypothesis is called alpha, level of significance, 1%. If we see something 1% or less likely, we're going to reject the null hypothesis. We're using the critical value method, and this is a two-tailed test. I would care if I got a very positive difference or a very negative difference for my x bar p minus x bar h. It could go either way. We just want to know if it's a difference. So it's two-tailed, and we split alpha between these two tails. The critical value is the z-score to exclude those. You may have a table of these. If not, use the inverse normal function. The critical value is plus minus 2.576 to 3 decimal places. Now I'm going to compare that to the test statistic. That's basically the z-score of our difference. It will tell me where on this curve it falls. Now to get that z-score, you take your raw value. So z-stat is the raw value, which is x bar p minus x bar h, minus the mean of this curve. Well, we think these are the same, so we think this is just 0. And divide by the standard deviation, which is this thing here. We don't have the population standard deviation, so we have to use what we do have. Now, keep in mind here that we're making an assumption that we are kind of pooling these as an estimate for a shared population standard deviation. Otherwise, you have to do a much more complicated non-parametric test And so we make this assumption so that we can actually do this. Okay, so on the numerator we have minus 12. On the denominator, I need to get these now, so 60 squared divided by 50 plus 80 squared divided by 50. Square root that, it's root 200. And I get minus 0.849 to 3 decimal places. Okay, that's not as extreme as our critical value there. So our sample mean difference thing does not fall in the rejection region. So the result here is we fail to reject the null hypothesis. The difference that we have found is not significant. So not a significant difference. It's extremely plausible to us that this could have just arisen due to sampling error.